Alright, hello everyone. Today I am going to follow up on a question from the previous video where we discussed a couple follow-up questions from the original video on how to calculate the distance to the sun. So the following statement or question was brought up as asking whether this is a potential issue. So I'm going to write this now. So the first possible issue asked was, are we taking advantage of the margin of error? By which the asker is referencing, are we abusing the original uncertainties we're assigning to measurements and therefore their resulting error? And the second concern is that since we are using 90-degree angles from Venus to the Sun to Earth and a flat solar system, we're now allowing ourselves to use sine theta m equal to x over 1 AU. This is one big assumption, is it not? So to answer these questions, we have to discuss the greatest fear of undergraduate physics students. Boo! Errors. It's errors. The thing that terrifies all undergraduate physics students. Because it's often not explained super well, or in a great amount of detail, and it's kind of glossed over. So we're going to use that here. So, okay, so what is an error? Let's first talk about uncertainties. This might be what you're referring to when we say margins of errors. Okay, so let's first talk about uncertainties. Or at least what I mean when I'm saying an uncertainty. So an uncertainty for me is when you make a single measurement and that measurement has some kind of reading error. So for example, if I have a ruler and this ruler has tick marks that have some reading, then if I have something I want to measure which doesn't line up exactly with a tick mark, then there is a limit to how accurate I can measure this thing. So for instance, this orange blob that I've drawn is greater than 4 and less than 5. So you might write this as being 4.5 plus or minus 0.5. Yeah? So this is what I mean when we have an uncertainty. It's just how accurately we can measure this thing. Now, when I say I'm talking about errors, I'm talking about the downstream propagation of the uncertainties we used earlier. So for all of the things we just read off, like this 4.5 plus or minus a half, we can take these uncertainties, like this 0.5, and figure out what their cumulative error is to the final calculation. So I wasn't showing that in these steps, but there's a specific set of rules. There's about 4 of them. We have a propagation error rules for addition, subtraction obviously, multiplication, and a more generalized rule which will show you how to do things like trigonometric functions, things like logs, or just any function f of x. So we have a set of rules that tell us how to do these. What the downstream error is going to tell you is taking the maximum uncertainty values for any combination of your measurements, what the downstream error could be. So say you have a bunch of rulers you need to measure, and all of these, perhaps the true value is actually 4.5. If you took the uncertainty value, say the minimum value of 4.0 for all of these, based on your reading, how much does that 0.5 uncertainty from, say, 10 measurements add up to the final result? So when we talk about the margin of error or the total error in a final answer, so long as we believe the uncertainties of all of the initial measurements and that we believe the uncertainties in those initial measurements are uncorrelated, then the final answer is giving you the range of possible values that you would measure if you were to do the experiment again. So for instance, when I'm looking at all of the uncertainties in our initial measurements, we have a 10% error in the angle, a 20% error in time, a 10% error in the period, and I believe these were all of the initial measurements that we made. So this is theta, this is time, and this is period. Now it is important that these are uncorrelated values. So what that means is that these errors can't affect your other measurements. So whatever we measure theta max to be doesn't affect how we measure time, and how we measure time of the transit period doesn't affect how we previously measured the period, right? These are three uncorrelated things. So these are truly independent values. And when we end up multiplying these, there's a couple intermediate steps. The way we find out the total error at the end is through a square root of the sum of the values. So we'd go the square root of 0.1 squared plus 0.1 squared plus 0.2 squared. And the reason why we were saying these had to be uncorrelated is because we're using a Pythagorean summation of the errors. So if our errors are uncorrelated, then we have this three-dimensional space of possible errors. So we have a delta theta, a delta time, and a delta period. And so we have these measurements a bit this way, we have a bit this way, and we have a bit upwards, and we want to know this total error. We want like delta epsilon. And the way you do Pythagorean distances is through the square root mean method. So the sum of these errors here give you about, I'll just write this as 25%. Now there were a couple of intermediate steps. So to get our final answer, we use theta to get x, and we used the period to get omega. And then we used the Venus-Sun distance, the time of the transit, and omega to get 1 AU. And so the key thing about all this is we kind of see this linear flow of uncertainties. We're not doubling up on our uncertainties out anywhere. None of these measurements had to affect the other measurements. So what that means is that this method of squaring, addition and quadrature, and square root, this method of adding up our uncertainties works. So what can happen is when we do a step like this, we can add more uncertainty along this direction, right? So if this value here was 10%, a step we do here might add to this specific error. So this might add, say, it might increase it from 10% to 12%. Okay, so my food just finished, and I had to go eat, so hopefully that didn't ruin my train of thought too much. So I think what I wanted to say was that because the errors that we're adding on in these steps only add linearly to the specific step, it doesn't throw off the final calculation by a lot. And I had tried to convince you that the amount that they even do throw it off is rather small, and if it wasn't, we would be able to see that. So for example, in the flat plane example, we were able to determine that the uncertainty that comes with this approximation is about 1%. So that would be a pretty small amount to include. For the 90-degree angle part, we know that as we get closer to a circle, it's going to be less and less of an effect. If you want, I can make a separate video where I will show you exactly how much percentage error it will give depending on the eccentricity of that orbit. But the key thing I was trying to point out in the last video is if you make many measurements of theta m, if there is little eccentricity and therefore very little error in theta m, then when you make these measurements of theta m, what you'll see is these peaks. Ooh, I had another one of those things. What you'll see in theta m is these peaks are all going to line up to the same height. If you have a large ellipse and therefore a large contribution to the measurement of x, then what you will see in your tabulation of theta m is a periodic change. You'll see a periodic change in your measurement of theta m. So you'll see large theta m's, smaller theta m's, and then back to large. So while you're measuring theta m, you can determine the uncertainty that comes in this approximation. And when you do this, you're going to find that Venus is nearly perfectly circular, and therefore very little uncertainty is accumulated by this 90-degree. Again, if you want, I'm more than happy to make another video showing you what this uncertainty will be for different ellipses. It's just, it will probably take me like a half hour to code. And right now, I have some research I need to do. So I'm only going to make that video if you need it. Okay, so the first question was, are we taking advantage of this margin of error? And then I have kind of already just dove into this sine theta bit. So let me just rerun through this because I took a dinner break and I'm not sure if I maybe missed some things. So are we taking advantage of the margin of error? No, the margin of error is a tool that we use to determine if we were to reproduce the experiment, what range of values would we expect to find based on the uncertainties that we expect from our measurements. The second statement was, again, since we are using 90 degrees and flat solar system, you are enabling yourself an entire right angle triangle to calculate x. That's a big assumption, is it not? So for this, I would just say that we can find out if it's a big assumption or not. So maybe I will just do this other video anyways, but we can show that assuming 90 degrees isn't a huge assumption if we know what the eccentricity is, which we can measure. And a flat solar system, we can see how much the inclination that we observe is going to affect our measurement. And that, for Venus, works out to be about 1%. And so those are not big assumptions, I wouldn't say. I'm running out of time for tonight to do this. So one thing I wanted to maybe just show that I think is neat about how good assumptions are sometimes. Also, when we say assumption, I'm really talking about approximations. We're not assuming things per se here. We're approximating one thing to be very similar to another. We're not going from nothing to right angle triangle. We're going from what might be like an 89-degree triangle to a 90-degree triangle. So maybe just a slight bit of wording to keep in mind. So here is something that is really cool. If you take a graph here. It's a great line here. And you draw sine theta. So how does this go? This is 90 here, right? So let's say I want to know the value of sine theta at, say, pi by 8, right? So this is, one sec, pi by 2 is 90, pi by 4 is 45, so then pi by 8 is going to be 22.5. Okay, so what is this value going to be? So I can either take sine of pi by 8, or 22.5 degrees, or I'm going to do a fun little math trick for you, okay? I'm going to say, right, so we know that pi by 8 is about 22.5 degrees. So if I wanted to know what the sine of pi by 8 is, I could either pull up my calculator and punch in sine of pi by 8, or 22.5 degrees, or I can approximate this to be, let me think here, this is 3.14 by 8, that's going to be about 0.4. Yeah. Yep. Okay. How did I do this, and how close am I? Okay, so calculator. Let's first find out how close I am. Sine of 22.5, 0.38. Okay, so in reality, this is actually 0.38. So this is 0.02 over 4, so this is over 0.4, so this is like 2 in 40, which is like 1 in 20. Okay, this is 5%. Because 1 in 10 would have been 10%, so 1 in 20 is 5%. Okay, so I was able to estimate sine of pi by 8 to be 0.4, which is within 5% of the true value. So how did I do this? Well, we have a lot of approximations in mathematics we can use, one of which is that sine of x is equal to x for small x. Now this approximation, the first time I saw it, I thought, okay, cool, I can use this for like 1 degree or less, right? But a lot of approximations that you can come across involving trigonometry work really well for surprisingly good theta. So sine of x equal x works actually really well, almost up to like 40 degrees, which is why I picked pi by 8. Okay, so this was almost unrelated, I would say, but maybe an example of how approximations can sometimes be very good, despite the fact that they are approximations. And so what sometimes might look like a big approximation isn't that bad at all. I had even less of a plan of what I was going to say this time, so I hope I said something useful, and hopefully you got something out of this, and I'm sure I'll be back with another video tomorrow, because you have a lot of questions that I can answer. So yeah, have a good day, a good tomorrow, whatever. Cheers.